Okay, hi, so today we're going to be evaluating another integral using the Riemann definition of integral. Well, this is the integral we're going to be doing. Well, I have already done the integral of the cosine of x this way. This is actually the first integral I've done this way for the channel, and you can go there and look at it, and I will explain things in more detail. Well, here we're just going to do it a bit faster. So, just a quick recap. The Riemann integral can be defined, well, it is the area under the curve, right, or between this curve and the x-axis, and we are going to divide this area into rectangles with base given like this for a definite integral and indefinite integral, and the ci is just the leftmost point of the integral. As we see, the definite integral can actually be redefined or interpreted as a definite integral between x0 and x, which is the variable. And t here just means that, well, it's just a matter of notation, so we do not get confused with this x. So we could not write x here again because we already have it here and it's confusing. So let's just do it. And well, this is just the limit when n goes to positive infinity of this sum, the sum going from I equals to 0 to n, of the sine of ci times delta x. But ci, as I said, is x0 plus delta x times I, so x0 plus delta x times I times delta x. Yeah. And well, we will call Sn equals to this sum I equals 0 up to n of the sine of x0 plus delta x times I. And notice that I have not included delta x here because we can actually take it out of the sum. We can put it here. Why won't we do this? Well, just explain real quickly. This delta x does not depend on I, so whenever we are adding up the terms, it is common for all of the terms in the sum, given, so we can actually take it out because it's multiplying all of the terms. So actually the sum is just this. How do we do it? Well, there's the method I'm going to be using, as I have read online on some articles and some sites. It was firstly introduced by Great Sarah. I will put the links in the description so you can actually see this method. But well, the thing is that we are going to use a trigonometric identity, which is this one, and this is actually really similar to the identity we use for the integral of the cosine, but because we're dealing with kind of a different function, we need a slightly different trigonometric identity. So here we have that the cosine of the sum minus the cosine of subtraction of two angles is equal to minus 2 times the sine of A times the sine of B. Well, we have only one sine, so we can multiply by minus 2 the sine of something, and if we do it there, we can actually just do it here, so the equality holds. What is the smart choice for this new angle? Well, the smart choice, after a lot of thinking by Grazer and after you can see that it works, is delta x over 2. So this is the smart choice for this angle. And you see that everything goes nicely if we choose this. Well, we have minus 2 times the sine of something times the sine of something else. If we call this A and this B, we can rewrite this using this identity. But just a small detail, we have multiplied by minus 2 delta x here, and we have taken it right inside the integral. Why can we do this? Well, again, minus 2 times the sine of delta x over 2 does not depend on I, so we can take it in and out of the sum. Also, this is not an infinite sum, so there's no problems about any of this. So, well, using this is just the cosine of the sum, so it is the sum from I goes to 0 to n of the cosine of A, x0 plus delta x times I, plus b is just delta x over 2, delta x over 2, minus the cosine of A, which is x naught plus delta x times I minus b delta x over 2. Well, here we can take out common factor delta x and just express this as, x naught plus, I plus 1/2. Minus the cosine of x naught plus 1, I minus 1/2, Let me just check for a minute, and yes, that's it. Okay, so what's so important about this sum? Why have we taken why have we bothered ourselves to multiply like this and get this result? Well, the thing is, this is a telescoping series, meaning that almost all of the terms cancel out, and we end up with actually just 2 terms. So let's see how this happens. Well, for I equals 0, what do we get? We get the cosine of x naught plus 1/2 delta x minus the cosine of x naught minus 1/2 delta x. Well, so far doesn't seem really anything new or anything helpful, but if we go to the next term, I equals to 1, we get the cosine of x naught and plus, 1 plus 1/2 is just 3/2 delta x minus the cosine of x naught plus 1/2 delta x. Notice that this term cancels with this term, so the first term here cancels with the second term of the next term of the, I'm using a lot of times terms, but I'm not too sure how to distinguish them, how to say it in another way. Well, now going for I equals to 2, cosine of x naught plus 2 plus 1/2 is just 5/2 delta x minus the cosine of x naught plus 1 minus 1/2, just 1/2. So, see the pattern, first one cancels with the second one, first one cancels with the second one, and if we keep on going, this first one cancels with the second one of the next one, and so on, until we get to, let's just go for n minus 1, and see that we get the cosine of x naught plus n minus 1 plus 1/2, n minus 1/2, n minus 1/2 delta x, cosine of x naught, n minus 1/2, minus 1/2, plus n minus 1 delta x. Well, just going up for the last term, where I equals to n, we get the cosine of x naught plus n plus 1/2, minus the cosine of x naught, plus n minus 1/2. This is a 2 delta x, and that's it. So let's just see again this pattern of the telescoping series. This first term cancels with this second term. Okay, so going for the next one, this first term cancels with this second term. Again, this first term cancels with the second one of the next term, which I have not written. And likewise here, the first term cancels with the second one. This first term cancels with this second one. And this first term does not cancel with anyone because there's no more terms. So we're left with this and this. Just 2 terms in the sum. Okay? So I'm going to erase this and rewrite it here. But let me just check just 1 minute that I have not made any mistakes. Yes, n plus 1/2. So n minus 1, n minus 1/2. Yes. Here it's just, see, this is not n minus 1. is minus 3 halves. Right? Yes. Yes, yes. Yeah, sorry, I made a mistake there. It's just minus 3 halves. So, I'm going to erase this and just express it here. So, you have the cosine of x naught plus m plus 1 half delta x minus the cosine of x naught minus 1 half delta x. Okay? Yes. Okay, so I'm just going to erase all of this. So the next obvious step is just, well, we want Sn, so let's just divide by this, but be careful. To divide by this, we have to assume that minus 2 times the sine of delta x over 2 is not 0. And this can only happen if delta x is not an integer multiple of 2 pi, which is just the set of minus 2, minus 1, 0, 1, 2, I'm not going to go into too much detail about this, but just it's what the algebra requires. In the previous video, the video about the integral of the cosine, you will see a little bit about the geometrical meaning of this. But it's just that, well, choosing rectangles with this base is not too convenient for us. Also, well, I just want you to think that delta x can be negative. For example, if x is less than x naught, or if it is a negative number and x naught is a positive number, this delta x is negative. But this negative base just means that we are taking the base to the left of x naught. As I said, here I'm saying it really quickly, but on that video, if you go to the different parts, there's one part which is dedicated just to this. So, assuming that this holds, or even better, assuming that delta x is less than 2 pi, which this is just saying that delta x is on the interval minus 2 pi to pi, well, delta x will never be 2 pi times n, okay, because if it's not 2 pi, neither minus 2 pi, so it cannot be 3 pi or minus 3 pi, and so on, okay? So this is actually a better consideration, I think, but both of them are valid. So, having this out of the way, we can divide and just say that Sn is nothing but the cosine of x naught plus n plus 1 half delta x minus the cosine of x naught minus 1 half delta x over, oh, I'm so sorry for that, I just write it here again, but just minus 2 the sine of delta x over 2, okay? So we will just replace this expression here and take the limit and see what happens. So this is just the limit when n goes to positive infinity of, well, my delta x times 1 over minus 2 sine of delta x over 2 times the cosine of x naught plus n plus 1 half delta x minus the cosine of x naught minus 1 half delta x, and that's it. Okay, it might seem ugly to put a negative sign here, but well, I just did to make things faster, because otherwise I will have to put a bracket and, well, it doesn't matter. So, taking out the negative sign, we can actually split this into limit of this term times this term. So the limit when n goes to positive infinity of delta x over 2 and the sine of delta x over 2 times the limit when n goes to positive infinity of the cosine of x naught plus n plus 1 half delta x minus the cosine of x naught minus 1 half delta x, and that's it. Well, first of all, let's start with that limit. This limit, if we make the following change of variables, I'm just going to call this L. So making the change m, okay, m is equal to x naught minus x naught over 2n. This, using this definition, is just, well, delta x over 2, right? So delta x over 2 is just this. If n goes to positive infinity, as is the case here, this implies that m goes to 0. So we can rewrite, sorry, keeps falling off my hands, L as the limit. When m goes, this new variable goes to 0, of m over the sine of m, which can be rewritten as 1 over the sine of m over m. Okay, I'm just notice that before taking the limit, m is not 0, so we can divide and do many things. Taking this limit, this is just the limit of the numerator over the limit of the denominator, and the limit of sine of m over m is just 1. I'm not going to prove it in this video. I will make a video proving it. I'm not going to prove it here. So we can just rewrite this as 1 over 1, which is 1. So all of this is just 1. Meaning that this integral is just minus 1 times this other limit. But what is this limit? Well, first of all, let's remember again that delta x is just x minus x naught over n. And it's not 0, okay? So just to make that clear. Then, well, we can rewrite this as, well, just this term here, n plus 1 half times x minus x naught over n. Distributing this here, this becomes 1 plus 1 over 2n. Okay, so, oh, I just erased it. Well, sorry for erasing it so fast. This is the cosine of x naught plus, distributing the n, 1 plus 1 over 2n x minus x naught. Minus the cosine of x naught minus x minus x naught over 2n. And, well, this is a really easy limit. Maybe when n goes to positive infinity here, this goes to 0. And this also goes to 0. So we have minus the cosine of x naught plus x minus x naught minus the cosine of x naught. Of course, x plus x naught minus x naught is just x. So we have minus the cosine of x plus the cosine of x naught. And this is the value of our integral. I'm going to write it here so I can erase this and make some fast comments about this result. So minus the cosine of x plus the cosine of x naught. Okay, so I erase this. And yes, well. Okay. Well, using your usual calculus theory, this is the same result you would get to if you use that the derivative with respect to x of minus the cosine of x plus the cosine of x naught is equal to the sine of x. This is how you will actually do it in a regular calculus course. You will say, well, we notice that this derivative of this is the sine of x, so it must be an antiderivative by the fundamental theorem of calculus. Okay? Yes, okay? Because the fundamental theorem of calculus tells us the derivative with respect to x of x naught and x of f of x, the x is just, I'm going to write it here t, as I have been doing throughout the video. Sorry, just, yeah. This is f of t, meaning that this, if we call it f of x, is the antiderivative of f of t. So from this, we would get, well, this is this, so x naught, x is sine of x, the x is just minus the cosine of x plus the cosine of x naught. That's how you would do it. Well, here you have used the derivative of the cosine, and well, of this is just the sine, which you would prove by using the definition of the limit definition of the derivative, which is a lot easier than just doing this sum. But of course, you will have to prove the fundamental theorem of calculus, and well, sorry, this is not a t, this is an x. Got mixed up there. And well, you would get into trouble proving this, where it will be longer. So this is another approach. As I said, I've made a video about the integral of a cosine, and I will be making more videos about other elementary integrals. Who knows, maybe I'll make some other harder integrals by this method. But, well, that's it for today. I hope you liked it. If you want to see more, just watch other videos.